Sure.
And Kashiyara-san went for exchange. I saw one paper he published with abroad.
Say again.
Kashiyara-san went for exchange for other lab abroad. I mean.
You mean after PhD?
No, during PhD, they go.
I see. Yeah, he joined a group of Cooperative at ETH.
Okay.
For quite some time, more than 6 months, I guess.
Okay, I saw some papers recently.
Yeah, he published one organic data paper, right?
Yes.
You might have seen that.
Yes.
Yeah, that was quite kind of different, new things for him, although still, related to organometallic chemistry, but completely different ways to study organometallic chemistry that he wanted to learn from the corporate group. Yeah, he will join the industry after PhD. He already had an appointment with a company.
Oh, nice to hear. So I think now in Japan around 8:40 night evening.
8:30. So it is 5 in your place, right?
Yeah, for us, 5 p.m.
Yeah, for me, it's a bit strange that we have a kind of, how many hours, but anyway, so there is kind of 30 minutes difference plus several hours. I have never seen such difference. I mean, always I see exactly 2 hours, 3 hours, 5 hours, whatever. But your place is like, I don't know, 3.5 hours.
Yes.
It's quite new for me. I mean, to see difference, including, 30 minutes, right? I mean,
yes.
Everywhere I have seen basically, exactly several hours.
Okay. So we can now start now. Hello everyone. Welcome to the Department of Chemistry, IIT Delhi. So thank you very much for joining today's webinar. My name is M. Ramu Yadav and I'm a webinar facilitator and an assistant professor at Department of Chemistry, IIT Delhi. And we are pleased to bring you this content today, which is part of the online Pratidhwani series that the department is organizing past 2 months. Under this Pratidhwani program, we invite eminent scientists from different areas of chemistry from all over the world. So they will present in 30 minutes their work and on every Thursday afternoon. So please do check out our webinar website. You can find coming lectures and also you can find the link to join the webinar today. So the webinar series is organized by Author Cafe. Author Cafe is an online platform that aids with writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with products like Mendeley, ORCID, cross-reference, and so on. So if you want more information on Author Cafe, please go there, check their website. So today we are delighted to have Professor Yoshiaki Nakao from Kyoto University, Japan, as our distinguished speaker. So before starting the webinar, there is a couple of technical announcements. So please do not unmute yourself during the presentation. If you have any questions, please type them in the chat box, and we'll try to get at least some of them through to the speaker after the talk delivered. So Professor Nakao pursued his PhD from Graduate School of Engineering, Kyoto University, working with famous renowned Professor Tamajiro Hiyama and Iji Shirakawa. During that period, he was also visiting student in the Professor John F. Hardwick at Yale University. Later, he was a visiting scholar in Professor Manfred T. Ridge at Max Planck University, Germany. In 2002, he was appointed as an assistant professor at Kyoto University and later promoted to associate professor in 2012. Followed by in 2014, he was promoted to full professor and currently is holding that position. So during this period, he has significantly contributed in the field of catalysis. In particular, cooperative catalysis, he showed very innovative paths for site-directed CH bond functionalization and also alkene difunctionalization. So his work has been recognized worldwide with several awards. I would like to name a few of them. He was awarded in 2010 Mark Banianu Lectureship Award, and in 2015 he was awarded Hetheden Young Investigator Award. So this is will be awarded to under age of 40 years who exhibited exceptional creativity and dedication in the field of organic synthesis. In 2018, he was awarded GSPS Prize, which is also one of the prestigious prizes in Japan. So today he is going to discuss with us CH bond functionalization by cooperative catalysis. A very warm welcome to Professor Nakao, and now your floor is yours.
Hi, everybody. Good evening, ladies and gentlemen. First of all, Ramu-san, thank you very much for your kind introduction and the kind invitation to tell you about our chemistry. For me, it's kind of very rare experience to give a lecture online. This is actually second time to give an online lecture, so I hope my lecture will work well. I hope you hear me well. If you have any problem, please let me know.
It is very clear.
Okay, good. So today I'd like to talk about CH functionalization by cooperative catalysis. And to start with, let me introduce some very brief introduction. So many of you might know the function of, in general, catalysis in organic synthesis. And when you use a metal catalyst, it interacts with your substrate to give some intermediate, and then that reacts with another substrate to give product. This is very much simplified catalytic cycle of some catalytic organic reactions. So I'd like to define here one particular type of cooperative catalysis, where I'd like to have 2 or maybe 3, 4 different metal catalysts together. And what we hope here is that several, well, 2 metal catalysts at least interact with your substrates simultaneously to give a species like this. That is doubly activated intermediate. And then we expect that such intermediates react with another reactant, finally give product. We hope that this kind of doubly activated species would show some completely new reactivity. And we have studied reaction development by taking advantage of such doubly activating cooperative catalysis. Also, we hope that we could control the selectivity of certain transformation by having such doubly activating cooperative catalysis. So today, I'd like to, my group has focused on such cooperative catalysis for the development of carbon-carbon bond functionalization, CH functionalization, and the CX functionalization. But today, I'd like to focus on CH functionalization by using transition methods such as nickel, iridium, and rhodium in combination with boron and aluminum as a co-catalyst. So, but let me again tell you about some now general background of CH functionalization. So CH functionalization is certainly the most important research topic in modern organic synthesis, because you can transform your compounds directly to your target product. But there is some still limitation in CH functionalization, particularly in terms of site selectivity. So you often need some directing group to control the site selectivity of your CH functionalization. Here I show the case of substituted benzene. So you may need ortho, meta, or para directing group to control the site selectivity. But such directing group has to be installed in your compound, starting from more common functional groups. And after CH functionalization, you actually need to bring these specially designed directing groups back to a common directing group, so that you can access your target compounds. But often, obviously, you need several multi-step sequences to achieve your transformation, even though taking advantage of CH functionalization here. So ideally, it's better that you can control the site selectivity of CH functionalization with common functional group, directing group, not by manipulating such functional group, but using catalyst to control the site selectivity. There have been many nice examples for ortho-selective CH functionalization, thanks to the pioneering work developed by Japanese chemists Murai and Kakiuchi. But there have been much room to be developed for meta and para-selective CH functionalization controlled by catalyst, not by substrate. So that's the goal we would like to pursue by taking advantage of cooperative catalysis. So then the question is how to do that. So in 2010, we reported that the pyridine can be alkylated at the C4 position in the presence of both nickel having this particular ligand and aluminum catalyst that is very bulky researched catalyst. So you can see that this is a completely C4 selective, at the same time linear selective reaction. So the reason why here it is C4 selective is that pyridine binds to the bulky aluminum research sheet, and the nickel activates the CH bond at the C4 position. And here, steric repulsion between bulky aluminum research sheet and the ligand on the nickel controls the site selectivity. So we simply imagine that having such system, we could control the site selectivity of substituted benzene in the CH alkylation reaction. For example, we imagine that use of aromatic carbonyl compounds could also coordinate to a bulky aluminum research, and then the nickel could control the para-selectivity of this CH alkylation reaction of substituted benzene in derivatives. So that was our initial kind of idea to pursue the catalyst-controlled para-selective CH functionalization. So to do so, we took benzamides as a substrate, having obviously a least basic functionality here, and then that was reacted with alkenes in the presence of a nickel and bulky aluminum research sheet again. Here, actually, we used a stoichiometric amount of the aluminum research sheet. the use of the ligand that I showed in the previous slide for pyridine functionalization showed very poor yield, but quite some promising site selectivity favoring para-alkylation reaction. Notably, there was no auto-alkylation in this case, which is quite common with other metal catalysts, because as I already mentioned that it is common that such carbonyl groups directs the metallation at the auto position through coordination of the carbonyl to the metal catalyst, but that was not observed in our system. Encouraged by this result, we started to look at the other ligands. When we put bulkier substance here, we could see the increase of yield, but the site selectivity was not improved. And then we started to look at the other substance on this ligand. When we put methoxy here, making the ligand more electron donating, we could see some improve of yield, but no selectivity improvement. Then we started to put a substrate at the phenyl groups at this peripheral region of the ligand. When we put methyl here at the para position, we didn't see any improve. But to our surprise, you could see very nice yield, at the same time quite nice para selectivity when we put 3,5-dimethyl groups at this peripheral phenyl rings. It was, at least at that time, quite surprising to see substituent effect dramatically observed at this peripheral region of the ligand. Because normally we see substituent effect near the metal center. We expect that the metal Nakao is here, so that it was a bit surprising to see substituent far from the Nakao center affects the reaction efficiency and the selectivity. Well, anyway, we also looked at the effect of Lewis acid, and certainly bulky Lewis acid catalysts are important to control the para-selectivity, and the use of just trimethyl aluminum or the absence of Lewis acid showed poorer yields and para-selectivity. So here I would emphasize that the site selectivity control para-selectivity is cooperatively controlled by both this particular ligand and the bulky aluminum Lewis acid. I here show a brief summary of our substrate scope. You can see that the different benzene substrate are alkylated at the para position selectively, even in the presence of possibly competitively Lewis-based alkoxy carbonyl groups and pyridyl nitrogen, sp2 hybridized nitrogen, which was actually a kind of directing moiety to control the C4 selective alkylation of pyridine derivatives. But here you see the para-selectivity relative to the amino carbonyl group. We also looked at the alkene substrate. You can see that the different alkenes can be introduced to give the corresponding para-alkylated benzene product. We looked at the mechanism by DFT calculation, collaborated with Professor Sakaki in your school, and it has been proposed that this alkene Nakao complex is a resting state, and you have a ligand exchange between alkene and benzene amines coordinating to a Lewis acid to give sigma complex here. CH functionalization takes place from this in species through TS like this to give early alkyl Nakao intermediates. This is so-called ligand-to-ligand hydrogen transfer mechanism, which is quite unique to the Nakao system. Because normally you could expect that two-step processes such as oxidative addition CH followed by migratory insertion of alkenes, but these two steps proceed in a single step with Nakao catalyst. Anyway, you have some isomerization of the early alkyl Nakao intermediates to end up with CC bond forming reductive elimination. This is a whole picture of the proposed catalytic cycle. As you can see that the CH activation step has the highest barrier to overcome that matches well with experimentally observed kinetic isotope effect. This green line represents the pathway in the absence of aluminum Lewis acid. You can see that the CH activation is significantly accelerated by the presence of Lewis acid co-catalyst. So then why is so para-selective with our particular ligand? So we looked at the TS for CH activation. This is para-CH activation. The other one is meta-CH activation. You can see that in the case of meta-CH activation, there is possible steric repulsion between methyl group derived from phenyl at the peripheral region of the ligand. You see that the 3,5-dimethyl group here, and then the repulsion between that methyl and the methyl from aluminum. And in real system, we actually use even bulky aluminum Lewis acid so that this steric repulsion can be even severer, so that the meta-CH activation could be, unfavored over this para-CH activation. So that's the reason why we could control the para-selectivity having ligand having with methyl groups here. To support the effect of alkyl groups here, we tested other derivatives. So I already showed the result with methyl, but when we increase the size of this alkyl group, we could see even better para-selectivity. And then even site selectivity at the even farther position could be controlled by using this ethyl ligand. You can see that by changing methyl here to ethyl group, then we could see improved site selectivity of these naphthalene substrate. So having had some para-selectivity control with benzene substrate, we naturally looked at other carbonyl derivatives. First of all, aromatic ketones could be actually alkylated at the para position selectively in the presence of bulky MAD co-catalyst. You can see that actually site para-selectivity at the same time, reaction efficiency could be better with the presence of this aluminum catalyst. In the absence of MAD, you see poorer reaction rate and also poorer site selectivity. Not only carbonyl, but sulfone amides could be handled to control the para-selective CH alkylation reaction. You can see again the presence of MAD allows nice para-selective selectivity. At the same time, reaction acceleration when you compare with the reaction in the absence of MAD. Finally, we also looked at anilids that has a carbonyl Lewis basic moiety one atom further when you compared with benzene substrate, right? In this case, we actually needed some, bulky substituent on the nitrogen to assist the, steric repulsion between Lewis acid and the Nakao catalyst. But with this particular substrate, we still could control the para-selectivity, and you can see the action acceleration in the presence of MAD ligand. So we have successfully, achieved para-selective CH alkylation of substituted benzene derivatives. Then we started to be interested in other CH functionalization to control the site selectivity. One particular CH functionalization that was interesting for us was a CH polylation reaction catalyzed by iridium. This work was, of course, pioneered by John Hartwig, Murder, and Smith III, and others. And nowadays, this is a very practical and useful reaction as a CH activation reaction, because you can transform the resulting CP bond to a different functional groups easily. So that this is, although two steps, but you can efficiently convert CH to useful functional groups. So this reaction is quite site selective when you have a substrate like this. So this iridium catalyst is sensitive to sterics, so that you can volylate the least sterically hindered CH bond. But the situation can be, difficult when you have a sterically less biased substrate. For example, 1,2-disubstituted benzene actually gives mixture of these two products. It is very tough to control the site selectivity here. For example, actually, when you take a benzene, a benzoate as a substrate under the common reaction conditions for CH polylation, you end up with a mixture of meta and para-polylated product. No control at all under the original reaction conditions. We hope that we could control site selectivity of this CH polylation by taking advantage of our cooperative catalysis. So we looked at the polylation of benzene mice in the presence of MAD again. So to make a long story short, we came up with the use of this particular BP ligand that gives a very nice para-selectivity. It seems that the steric bulkiness at the peripheral region again is important to control the para-selectivity, because this one gives some para-selectivity, but the di-T-butyl BP ligand gave very poor site selectivity. We still don't know why these sterics at the peripheral region affects the para-selectivity, but anyway, we could have a nice, good system to control the para-selectivity for the CH polylation reaction. So started to look at the system in more detail. So here again, I show a very rough kinetic profile of this reaction. You can see that MAD not only controls the para-selectivity, but also accelerates the reaction quite much. You can see that the absence of Lewis acid showed very poor conversion, and of course, no site selectivity control at all. Thanks to quite high functional group tolerance associated with the iridium system, you can have a quite nice substrate scope of benzene mice. You can see that even the presence of halogens are tolerated. You can also change the Lewis basic moiety to phosphonate, still giving the product having boron substituent at the position para to the aminocarbonyl moieties. The only limitation in this system is that when you have a substituent at the meta position, then this is sterically demanding to control the para-selectivity, so that the substrate control overrides the catalyst control, unfortunately. Except for the case of fluorine, that actually somehow directs the metallation at the para position. So we have succeeded in the para-selectivity control for the polylation reaction now. So again, taking advantage of possibly steric diversion between bulky aluminum Lewis acid and the metal catalyst. So then the question is how to control the meta selectivity with cooperative catalysis. So our naive idea was that just tethering Lewis acid moiety and the iridium center, or maybe Nakao, we could control the meta selectivity now rather than para selectivity. That was our next target to pursue. So we took benzene mice again to see the polylation now to control the meta selectivity. And to make a long story short, we came up with the use of this particular BP ligand having tethering aluminum Lewis acid in this way to perfectly control the meta selectivity of this polylation reaction. The structure of this aluminum moiety seems to be important because when you miss one phenoxy moiety here, you see the loss of meta-selectivity. And then when it is benzylic alcohol, we see poor meta-selectivity. And of course, when you put aluminum the other way around, you don't see any selectivity control. So again, the use of this particular ligand is crucial to control, not only control the meta-selectivity, but the reaction acceleration. As you can see, when it is boron, OH, or alkali metals, you don't see any, efficient selectivity control nor the reaction acceleration. So substrate scope is similar to what I already showed you in the paraselective polylation reaction, but now you can install the boryl moiety at the position meta to the aminocarbonyl moiety. I should mention that the meta-selective CH polylation has had some other strategies to be controlled. For example, hydrogen bonding could also handle the polylation of benzenides at the meta position. Also, Phipps took advantage of ion pairing to control the meta-selectivity of some charged substrate. We hope that our Lewis acid strategy could be complementary to these ways, taking advantage of non-covalent interaction. But our hope is that the Lewis acid can be better than these in terms of electronic activation of substrate because of stronger, interaction with substrate to, make the RM moiety electronically more activated. So, because I started this lecture from pyridine functionalization with Nakao, I would like to come back to pyridine functionalization. Pyridine is, of course, an important structure in organic synthesis, organic chemistry, whatever. But this is, this has some characteristics like electron deficient arenes. Oops, I'm sorry, it's something wrong. It should come back here. I'm sorry. So because of electron deficiency, you need some, limited way to functionalize pyridine core. It is known that the nucleophile radicals could be reacted to the pyridine to control the C2 selectivity or C4 selectivity. But these reactions suffer from harsh reaction conditions and modest site selectivity. Electrophiles could be reacted at the C3 position, but this has a poor scope because of these acids could be killed by the pyridine coordination. C4 selectivity control needs some multi-steps, including activation of pyridine followed by reaction with nucleophile or electrophiles. So we hope that we could control the site selectivity of pyridine functionalization, in particularly polylation reaction. Again, the original reaction conditions suffer from poor site selectivity. You end up with a mixture of two polylation products. So we looked at a reaction in the presence of bulky aluminum research, and we are happy to see that Lewis acid nicely controls the C4 selectivity of the pyridine polylation, as well as some nice reaction acceleration. You can see the scope of pyridine is quite nice with nice C4 selectivity now. You can tolerate halogens, and you can have a phenyl group here. You don't see any polylation on this phenyl, but you only install boron at the pyridine moiety. BP ligands could be functionalized, but again, the limitation is that the steric hindrance overrides our catalyst control. So we could not control the C4 selectivity in this particular case. So then the question is, how can we control the either 3 or 5 selectivity of pyridine polylation. So to make a long story short, again, we came up with Lewis acid tethered now boron instead of aluminum ligands to control the kind of meta-selectivity control of pyridine polylation. This shows a very nice C5 selectivity control of picoline polylation reaction. Again, other ligands having one methylene more or just conventional ligands do not control the such selectivity. So again, I emphasize that the importance of Lewis acid is not only site selectivity control, but also reaction acceleration of the CH polylation. You can see the scope is nice. You can tolerate different this basic moiety, also phenyl group moiety is inert under these conditions. You can install boron exclusively at the pyridine moiety. So we have been successful for the controlling polylation at the C3 and the C4 position. What about C2 polylation? Actually, 2-boryl pyridine is not always useful because it is known to be unstable under many reaction conditions. It is easily hydrolyzed to give the just protonated product. So we thought that C2 polylation will not be so useful. So we turned our attention to the silylation reaction because pyridyl silane could be even much more stable than the 2-boryl pyridine. And it is also known to be converted to many different functional groups by known transformations such as cross-coupling reaction. So I have shown that the strategy for the pyridine functionalization at the C4 and the C3 position, and how to control the C2 position. So we came up with the use of bimetallic catalyst that has a metal-metal bond here. We are actually currently interested in such metal complexes having metal-metal bonds because you could expect electron donation from this group 13 element to the transition metal center, at the same time Lewis acidity of this element. We are actually working on some quite different types of transformation by using that kind of catalyst. And among different group 13 elements, actually the combination of aluminum and rhodium seems to be promising because it has shows the highest charge separation. At the same time, you can expect higher Lewis acidity and a higher coordination number with aluminum. So I think I skipped this part. We designed this complex and synthesized this aluminum rhodium bimetallic complexes successfully. And we took this complex for the actually, first of all, alkylation of pyridine. This is a quite nice transformation in terms of selectivity, and at the same time, you don't see any double alkylation here. We have actually succeeded in the isolation of this complex derived from oxidative addition of pyridyl CH across rhodium and aluminum. And then we find actually we could develop the silylation reaction of pyridine again selectively at the C2 position of pyridine using a similar bimetallic complex. You can see that this has, I showed just as a brief summary of the scope of this reaction. You can install silyl group at the C2 position exclusively, even in the presence of some substituent on the pyridine ring. You can note that when you have a substituent here, you don't see any silylation. That is limitation, but characteristics of this system. Because when you have a methyl here, it is sterically demanding to allow the coordination of pyridine center to the aluminum center. So the mechanism should involve the coordination of pyridine to the aluminum center, followed by the oxidative addition, as I already showed you. And then you have some reaction between hydroxide and alkene, that is hydrogen acceptor, to give pyridyl silyl intermediates that gives silyl pyridyl product. We have studied this mechanism by experiments and calculation to confirm that this complex is likely a resting state. So we have achieved now site-selective functionalization of pyridine. What about saturated system? Can you do that? sp3ch functionalization can be more challenging, and even challenging is the site selectivity control. And it would be even nicer that you could control the enantioselectivity of this transformation. So we started to look at this kind of quite challenged transformation by using substrate having Lewis basic amide functional groups. So again, to make a long story short, we came up with the use of this particular pyridine substrate that could be borylated at the C beta position selectivity only in the presence of bulky aluminum Lewis acid. So this is the scope. I go this here quickly. You can borylate the position beta to the nitrogen, not only with 5-membered rings, but 6-membered ring. And you can see very nice diastereo selectivity when you have a substrate on this pyridine substrate. So the question is how to control the enantioselectivity. Of course, you can imagine the use of chiral ligand, right? So this was actually investigated first by Lamousan. He actually was very much, suffered from very modest enantioselectivity with this ligand, and when he made this type of ligand, he didn't see any reaction. That was very annoying project for him. So then, after he left, we came up with the idea to use chiral aluminum Lewis acid. Actually, we came up with the use of this particular chiral Lewis acid that controlled the enantioselectivity of this sp3ch polylation reaction. Here is one more example for this type of transformation. You can see a nice enantioselectivity with this particular Lewis acid. And we believe that this kind of product could be useful for the synthesis of some drug molecules. Enantioselective sp3ch polylation has emerged recently as a quite innovative transformation, but still limited to some specific substrates. So we hope that our strategy taking advantage of cooperative catalysis could be complementary to these known methods. So with that, I hope that I have convinced you that site selectivity control of CH functionalization can be nicely achieved by taking advantage of doubly activating cooperative catalysis. So we are still trying to develop further the different combination of metal complexes to develop new reaction and also selectivity control of CH functionalization and other challenging transformation. Finally, but not least, I'd like to thank my coworkers who made significant contribution to this work, experimentally and intellectually, and also funding agencies shown here. And finally, thank you for your kind attention. Thank you very much.
Thank you, Professor Nakao Sensei, for your insightful and stimulating talk. I hope our PhD students might motivate their response to this lecture. I hope you will accept some questions from the audience.
Sure.
So I see one question from Tommy Siddhanta. How easy to handle this aluminum based Lewis acid to perform the reaction, whether it's a stable or
could you say again how easy what?
How easy to run the aluminum based reagents in the catalysis? Means you can run in the open air or in the
okay. This our system is certainly actually sensitive very much to moisture and air. So we normally need to set up the reaction in a grow box. And yeah, it is limitation of our methodology, certainly.
Another question from Professor Subrata Kundu. How important is the aluminum-based bulky Lewis acid? Was tris-pentafluorophenylborane used in the place of the bulky aluminum Lewis acid for para-functionalization of pyridine?
Yeah, actually, we looked at many different Lewis acid co-catalysts, including what you mentioned, tris pentafluorophenylborane. But so far, I think aluminum Lewis acid only work well, particularly the bulky MAD. I think aluminum Lewis acid that we use quite crucial in terms of strong Lewis acidity, and of course also sterics is very important to control the site selectivity. So so far we have never succeeded with some boron-based Lewis acid, except for that I showed in the pyridine borylation reaction. Yeah, in many cases, probably aluminum's Lewis acids are more acidic than boron Lewis acid. And yeah, in terms of bulkiness, we so far need some very bulky phenol-derived substituent on the aluminum.
Okay. And there is another question. Can we replace NHC carbene ligand with CAT type carbene ligand?
What type carbene you said?
Cyclic alkyl aminocarbene. CAT.
Okay. Yeah, again, we have, of course, looked at such different carbenes, including, yeah, CAT type, right?
Yes.
If I understand correctly. Yeah, they didn't work actually. Well, we actually hope that the CAT could be a better NAC because it is probably more electron donating. But so far we have never had success with CAT ligands.
I hope this answers question. And one more is that in case of para-meta selective CH functionalization, mainly used with alkene as a coupling partner. Why not like arylation coupling partner?
So we haven't looked that much with arylation reaction, because when you think about arylation, you need some aryl nucleophile or electrophile, right? And then our system is kind of addition type. Our system is quite good at addition type chemistry, and also in the case of borylation, you just release borane having BH. But when you think about arylation reaction, you may need base to remove HX when you have when you use aryl halides, for example, aryl electrophiles. And when your relation is with aryl metals, you may need some oxidant, right? And so far, yeah, as I said, our system is quite sensitive to functional group tolerance is not that good. So arylation, which is necessary to use base or oxidant, is not so far, good transformation with us. So we are so far successful with transformation, which doesn't need any, additives like base or oxidants. We have tried some alylation reaction, but because of that reason, we haven't had many, investigation yet. But it could be possible that when we change the, metal systems, not with nickel or iridium, but to some palladium or other whatever, which are known to be good for alylation, we may be able to have some side selectivity control. But that has not yet been well, characterized.
I think that's a very useful answer for that question. This actually lecture will be recorded and it automatically can watch in the YouTube also. Somebody misses point, it will be available anytime in the YouTube. We'll wait 1 or 2 minutes if somebody asks a question. Is it okay, Nakao?
Yeah, sure.
So I think there are no more questions. So I
Professor
would
Ramo, yeah, am I audible? So, I had one question which is difficult to write, so I thought that if possible I can ask.
Yeah, Professor Nakao Sensei is our colleague, Subrata Kundo. He want to ask. Yeah, please go ahead.
Yeah, so I was looking, as I said, that the cyclic alkyne carbine, and so, but I found that with the bulkicity and also the sigma donation power, the catalytic activity increased. Right? So I'm sure that you have tried with the various kind of phosphine also. So, but then with the bulky phosphine and sigma donating, with very sigma donating properties, how is the different actually with this system, with the carbon system?
Yeah, so we of course also checked phosphine ligands. That didn't work. And I will go back to my mechanism slide, I guess. And in the case of alkylation reaction, actually, reductive elimination step is also has quite some barrier to overcome. You can see that I said that the CH activation is the rate determining, but you can see that the CC bond forming reductive elimination has also certain barrier to overcome. And this step actually needs some steric bulkiness to promote the step. I think phosphine is not good enough to promote this reductive elimination step in terms of sterics. With carbine, you could have a influence of sterics to very much to this allyl and alkyl moiety, so that the reductive elimination could be accelerated. So that's our current interpretation with the poor result with phosphine ligand. And we have also studied alkylation reaction. That is, the reaction with CH with alkynes to form vinyl arene products. In that case, we have seen that some phosphine ligand works, because probably when this is reductive elimination from two sp2 carbons, then it is much easier than the sp3 sp2 CC bond formation. In that case, I think phosphine works. But in this case, actually, you need a bulkiness to somehow accelerate the reductive elimination step.
Yeah, thank you, Professor. I understood. I agree. Phosphine are not so bulky compared to when you compare with the NAC and that too huge functionalization. Yeah. And one more thing, like in the last, when the metal cooperative effect, again, like the aluminum came.
Yeah.
So aluminum basically acts as a Lewis acid and takes the electron density from the metal, or like or it has something to do in the bond formation process also.
Yeah. Thank you very
I
much.
mean the direct effect on the bond formation.
Yeah, I think it is first of all Lewis acidic point. So to bind to the pyridine substrate, as I showed in the mechanism slide. So it is important that you accommodate pyridine substrate through Lewis pair formation here. And we think that this aluminum doesn't abstract electron from rhodium, but it is probably opposite, making rhodium even electron richer. Because aluminum, when it is, it has a covalent bond between rhodium. This is such an electron positive element, so that it doesn't, take electron from rhodium through covalent bond. So the role of aluminum is through this bond is to make rhodium electron richer. So this has two roles. So when rhodium is electron richer, it is more reactive to CH activation. So it has two roles. First of all, Lewis acid, and also making metal center electron rich to promote bond activation process.
Yeah. Okay. Thank you very much. Yeah, it's very interesting actually.
Thank you very much.
I think in that case, the aluminum is very specific over here. We cannot replace it with other elements like boron or let's say gallium in the same case.
Yeah, thanks for the point. So we have already actually looked at the boron here and the gallium here, and they don't catalyze this kind of transformation. Well, very much poorer than at least aluminum. So we think that actually the aluminum is the most Lewis acidic among group 13 elements that we examine. And in terms of electron richness of rhodium, I think boron and gallium is also a good ligand. But if you think about, just simply, electron negativity, aluminum has the least electron negativity among group 13 elements, I think. So that's our interpretation that aluminum works specifically among other group 13 elements.
Yeah, Professor, thank you.
You are welcome.
I think we can stop here, and I would like to take this opportunity to thank Professor Nakao for Nakao Sensei to accept our invitation and presenting this wonderful work to the webinar. And I would like to also thank our department head Professor Anil J. Elias and Professor Ramrab Swami for their encouragement to conduct such events in this pandemic. So our next talk of the series will be delivered by Professor Martin Jensen. He's an honorary professor at the University of Stuttgart, Germany, on March 11, 2021 at 4 p.m. So to get this link to join the webinar will be available on our website. And particularly there we are requested students to register to avail for certificates. We will provide special certificates to the students who will attend at least 10 talks of this series in a year. I think I will thank all the audience participants who attended this webinar. We hope to see you all soon. Have a great evening.
Thank you.
Thank you, Nakao Sensei.
So do you close? I just finished my sharing my.
Yeah, I think we can close. It's too late for you already. 9:30 p.m. See you, Nakao.
Okay, thank you very much.
Thank you.
Good luck with your research. I look forward to seeing your papers.
Yeah, thank you. And if everything goes well in the future, we would like to invite you in person to present your research work in the Department of Chemistry.
Thank you very much. Same to you. When you become a rising star, we will be happy to, invite you to come to Japan.
Thank you.
I'm looking forward to that time.
Thank you, Nakao.
Yeah.
Yeah.
All right. See you.